Okay.
Yeah.
Oh.
Okay, good. So since Vera is not here, or is she? No, she's not here. So a big news came yesterday. Maybe it was announced officially earlier than that. I learned about it yesterday. Vera was awarded how it's called Christopher Hyde Medal from the Australian Academy of Science. Vera is one of the organizers of our series of seminars. Oh, Vera is here. So maybe she was unaware. Let me repeat. Vera, congratulations on your award.
Thank you, thank you. Sorry, we had a reading group, so some people a little late.
So you're not reading at the moment, so you are listening. So accept our sincere congratulations. I think it's a great success, obviously. And for our audience, of course, it's important to know that this is a reward for Vera's contribution to optimization research. So it's a sign that maybe optimization is finally getting some recognition on the government level. Okay, some flowers are appearing, applause, etc. Okay, so do well, keep collecting medals, and we will be happy to keep celebrating every your achievement.
Thank you, Alex.
Now probably it's start the topic. So we have a presentation by two presenters, Marianne Fabian, who already presented at our seminar earlier, and his younger colleague, David Bartl. They're both from the Czech Republic, which is suffering from COVID now. We already discussed this issue. David is not from Prague. He is going to present, as far as I understand. He is from Silesian University in Opava. I have very vague vision of the map. We found out that it is not so close to Prague. So anyway, the topic is, in a sense, continuation of what Marianne talked about at our seminar, and I see that they've made some advancement in this topic, and we are looking forward to learning about this advancement. Please, David, the floor is yours.
Oh, yes. So thank you very much for your introduction. So please let me start the presentation. So today or now I should present the result of Marianne Fabian and me, that every compact convex set of matrices is the Clarke Jacobian of some Lipschitzian mapping. So the outline will be that I shall introduce basic concepts, introduce the question and pose the answer. Then there will be intermezzo with 5 lemmas, what we call rayfish construction, and it will be extended to colony for line segment, and polygonal chain, and finally the coronal construction. And the finale will be the main theorem, and it will be proved meantime, during the talk. So the introduction. So elementary concepts, F Lipschitzian mapping. This means that this inequality holds for every x and y for some positive constant. The norms are considered to be Euclidean. Euclidean vector space Rn Rm is identified with the space of column vectors of the respective dimension n and m components. Next, every matrix of type m by n induces a linear mapping by this formula, and conversely, every linear mapping from Rn to Rm is induced by a matrix, so that we have this identity for every x. And this is the reason why we shall identify each matrix A with the respective linear mapping which it induces, and vice versa. By Rademacher's theorem, given Lipschitzian mapping F, it is Gateau, hence Fréchet differentiable almost everywhere with respect to the n-dimensional Lebesgue measure. That is the Jacobian matrix of these partial derivatives is defined almost everywhere for almost all x's, and as we said on the previous slides, this Jacobian matrix can be identified with the Gateau derivative, which is the linear mapping from Rn to Rm. We introduced the Bouligand Jacobian of a Lipschitzian mapping at a point x0. So it is the set of all matrices or all linear mappings from Rm to Rn, such that this matrix is a limit of the Jacobian matrices at points xk. Those points xk converge to the point x0, and the function must be differentiable at those points xk. And by Rademacher's theorem, this is good definition. And since this set is a collection of matrices, it is identified with the collection of the corresponding linear mappings from Rn to Rm. And finally, we introduce the Clarke Jacobian of a Lipschitzian mapping as the convex hull of the previous Bouligand Jacobian. So it is known, it is easy to see that the Clarke Jacobian is a non-empty set. It is a compact, that is a closed and bounded set, and it is also convex. So again, the Clarke Jacobian can also be seen as a collection of linear mappings from Rn to Rm. And the question which we try to answer, or which Marianne came across and found the answer. So given a non-empty compact convex set P of matrices, we ask whether it is a Clarke Jacobian of some Lipschitzian mapping G at some point x0. In other words, we try to characterize those non-empty compact convex sets of matrices that are the Clarke Jacobian of some Lipschitzian mapping. So our answer is that given a non-empty compact convex set of matrices, there exists a Lipschitzian mapping G such that it is the Clarke Jacobian of this mapping, perhaps at 0 or at the origin, or otherwise we can shift the mapping easily. So the answer is that every compact convex set, non-empty, can be a Clarke Jacobian of some mapping. And we actually prove even more. So first, we introduce concepts to put the question and the answer. So first, consider a linear subspace, non-trivial, like a plane or hyperplane and so on. And in the following, as said, we identify the matrix M and the linear mapping Lm, which it uses, as we said, and we use the same symbol M for both the matrix M and the mapping Lm. And by this symbol, with the restriction on the subspace W, we denote the linear mapping which is restricted onto the subspace. That is this linear mapping with this domain W. Similarly, given the non-empty compact convex set P, then by this symbol, with the restriction to the subspace W, we denote the collection of the restricted linear mappings, like this, of course, in the same manner defined. And finally, given also the Lipschitzian mapping G, then by this symbol, we denote the restriction of G onto the subspace W. Yeah, so its domain is restricted. And since we identify the Clarke Jacobian with the respective collection of the linear mappings, so we can define the Clarke Jacobian even as a collection of mappings from the linear subspace W to Rm. So we can define the Clarke Jacobian accordingly, even if this subspace W is not parallel with the coordinate axis, but it is a general subspace in the space Rn. And finally, the extended answer is that given a non-empty compact convex set of matrices P, there exists a Lipschitzian mapping G such that for every linear subspace W, the Clarke Jacobian is equal to the given set of matrices and restricted onto the double subspace W. So the equality holds for all possible subspaces, W being equal to the space Rn is the original answer before as a special case, but we have equality for all possible subspaces of all possible dimensions, non-zero dimensions. So these are basic concepts. And now I should introduce the important constructions. So first, simple concepts. We say, or we define, that given a mapping F, so we say that it is finitely piecewise affine if there are finitely many piecewise disjoint non-empty open sets omega 1 up to omega k, such that the complement of their union has Lebesgue measure 0, and there are matrices and constant vectors such that we have this equation, this identity. Yeah, so it is equal as a linear plus a constant mapping on some set, and it is piecewise affine. So simple observation, this mapping F is also Lipschitzian. Yeah, and the Lipschitz constant is the maximum of the norms of those matrices, which are seen as the respective linear mappings from Rn to Rm2. So we define the norm of the matrix as the norm of the corresponding linear mapping in the usual manner. And the derivative of the function f is equal to the respective matrix on the respective segment of the space, yeah, on this set. we also recall that the rank of a matrix is the maximum number of the rows of A that are linearly independent. And next, we consider matrices P and Q such that their rank is equal, the rank of their difference is equal to 1. We then say that that such matrices P and Q have continuous contact. So then we observe that the set H of points such that we have this equality is a hyperplane, and we call this hyperplane the hyperplane of the continuous contact of these matrices P and Q. It is hyperplane because the rank of the difference is equal to 1. So we have one row linearly independent. And now we start to describe the ray-fish construction, or what we call ray-fish construction. So first an exercise, we consider two matrices P and Q which have continuous contact, so the rank of their difference is equal to 1. We have the contact hyperplane, so since it is hyperplane, we take some normal vector to it, and we observe that this hyperplane can be expressed in this way also. And then we define some mapping F by this formula. It is driven by the matrix Px if it is left of the hyperplane, and Qx if it is to the right of the hyperplane. So this graph of the mapping F is depicted here, like this. It looks like a V-shaped, but two sheets of papers folded in the V-shaped, and it is Lipschitzian mapping and piecewise linear. So we introduce now the ray-fish construction for two matrices P and Q, and it is the first lemma. So let an alpha be given and let PQ be two matrices with rank either 0 or 1. Then there exists a Lipschitzian mapping denoted F alpha PQ from Rn to Rm, which is finitely piecewise affine and such that it is equal, it is linear and driven by matrix P outside of the unit ball, and inside of the unit ball it is defined somehow. We shall describe it on the next slides. And inside the ball there exists an open set, a ball perhaps, or just a non-empty open set, such that the derivative of the function f is equal to the matrix Q. It will be piecewise affine, so it will be Qx plus some constant. And moreover, the distance of the derivative from those matrices P and Q is less than alpha everywhere. Everywhere. Not only outside the ball it is equal to P, but inside the ball the construction is such that the distance is less than alpha everywhere. Whenever it is differentiable, so the construction is described here. So we prove the lemma. So let alpha and PQ be given. So first, if the rank is 0, then the matrices are the same. So we simply take the linear mapping, and the open set omega can be the interior of the ball, perhaps. So in the following, we consider that the rank is equal precisely to 1. So we consider the contact hyperplane HPQ, which is depicted here. And we consider the unit sphere in Rn, which is depicted here. So we pick a vector u such that it is orthogonal to the hyperplane, like this. And we observe that the hyperplane is the collection of the vectors orthogonal or perpendicular to the vector u. So we continue. Then we choose some delta, which will be manipulated later on. It will be made smaller, and we define the shifted hyperplane by minus delta away from the vector u. So it is here, depicted here. The distance between the hyperplanes is exactly delta. And we choose some points, any points, such on the hyperplane, such that they form regular simplex, and R delta J are the points which will be obtained so in such a way that you shift the hyperplane by delta away from the unit vector u. So here is the construction described formally, but it is anyway still the intersection of the hyperplane and the unit sphere, like this. So so we can see if the dimension is 1, that it is some trivial case, so we solve it in this way. In the following, we consider higher dimensions. So here we can see that we have several simplexes. So first, this large U, R, R, this large simplex, and also some smaller simplices, between 0, R, R, and U, 0, R, U, 0, other R's, and so on. So next, here is the construction finalized. So we have those matrices P and Q, which have the continuous contact. That is, when we take the hyperplane, their values coincide on the hyperplane. So if we shift the hyperplane by delta, then the values of some matrices PQ plus constant and QX plus constant will coincide on the shifted hyperplane, which is parallel with the original one. So we define the mapping in such a way that it will be equal to PX. It will be linear outside the ball and actually outside this large simplex. It is depicted here. And we define the mapping on the smaller simplices so that the mapping is continuous. So it is possible to solve some system of linear equations, and we just find the difference between the matrices P and Q. On this hyperplane, the difference would be 0. So here it is shifted. So here we must add or subtract some constant. This is a vector, so constant vector, so that it is continue here. And we also find new matrices, here denoted M delta 1, M delta 2, up to M delta N in general. So these matrices are found, calculated in such a way that this mapping is well defined, consequently continuous, and moreover Lipschitzian. So this is the main idea of the construction. So it is possible to find these matrices. So now we observe that as we let delta tend to 0, so as depicted, here it is larger, here it is smaller on the figure, so then the matrices M start to tend to the matrix P. So as delta is smaller and smaller, then here we have still the ocean of the values Px outside. Here on this small simplex, we have the slope of Q, and here the slopes are getting to tend to the matrix P. So it is getting to flatter and more flat. It is getting flatter and tending to P on these simplices. Everywhere. So the lemma has been proved in this way briefly. So indeed alpha was given, so we let delta tend to 0, and we just wait until the matrices M, delta 1, delta 2, or until the slopes are flat enough, enough close to the matrix P. So here it is a picture of rayfish in the ocean. Here it is detail, and here this is the reason why we call it rayfish construction, because of the resemblance with the rayfish. The tail is missing here perhaps, but here is the rayfish construction depicted. So outside is the ocean, the Px is the ocean, and this is the rayfish. Here we have the slope of Q. So some remarks. We observe that the derivative of the rayfish mapping F is in this mapping should be up to n. So QPM delta 1 to up to n whenever it is differentiable, because here the Clarke Jacobian of this mapping at 0 at the origin is the convex hull of these matrices, should be up to n, and moreover, if we take any subspace and we take the restrictions, then even we have equality with the Clarke Jacobian restricted onto the subspace and the matrices restricted onto the subspace also. So that's it. And here we have emphasized the set omega, which was specified in the lemma that it exists. So this is an open set such that the derivative inside the set is equal to the matrix Q. So it is taken in this small simplex. And now we proceed with the recursive rayfish construction. We call it rayfish colony lemma. So let beta and matrices Q0, Q1 up to Qk be given, and the matrices let have continuous contact. So that means the rank of the differences is less than or equal to 1. Then there exists a Lipschitzian mapping G, which is finitely piecewise affine, such that it is driven by the matrix Q0 outside the unit ball, and inside the unit ball there is a non-empty open set such that the derivative on the set is equal to the last matrix Q, and the distance of the derivative whenever the mapping G is differentiable, then the distance from this set of the given matrices is below beta. So let us describe the rayfish construction. So here we take the rayfish, we consider the starting pair of matrices Q0 and Q1. So we construct it, then we take the next rayfish. Now it is blue because the matrix Q was Q1 before, so now Q1 is matrix P now, and Q is Q2 as the next step. So it is this golden or golden orange color. So this is Q2 here. So next we take the matrices Q2, Q3. So Q2 is the ocean outside, and the green color now is matrix Q3, and so on, up to the last. It is still the last. Green is the next is some yellow color, or what is the shape? It is the last matrix, and you simply put each rayfish into this open set. You shrink the ball inside this ball of the previous rayfish. So the result looks like this, that this is the first rayfish taken. Here inside is the second rayfish with the matrices Q1 and Q2, and this very tiny is the third rayfish with the matrices Q2, Q3, and so on. It is very, very tiny inside. So this is the rayfish colony construction, because the rayfish are sessile. One is sitting on the previous one. So here we observe that as we go deeply, we immerse into the sets into which we placed those rayfish during the construction, we encounter all the derivatives, Q1, Q0, Q1, Q2, up to Qk on the last. And moreover, as delta tends to 0, then all these matrices M tend to the respective matrices, the outside Q0, here it tends to Q1, here on the smaller inside it tends to Q2, and so on. And the last matrix is fixed, actually. So, and now it follows that since the matrices tend to the matrices Q, then it follows that the distance of the derivative will be smaller than beta, from this collection of matrices, because the derivative can be either those matrices Q on these small simplexes, or it will be equal to one of these matrices M, but these matrices M tend to the matrices Q, so the distance will be less than beta if delta is sufficiently small in all of the rayfish functions. So And the set omega, whose existence is postulated in the lemma, is the very, very, very last, very, very small set omega in the very inside, in the very last ray fish inside. Yeah. So that's it. Next, we go back to the question, to the original question, that we wish to show that any compact convex set of matrices, non-empty set of matrices, is the Clarke Jacobian of some Lipschitzian mapping. So we must consider something more general. So from now on, we consider any two matrices, and we will extend the construction for general matrices. It will be for a line segment, construction for a line segment. Yes, excuse me. So this is the next slide. So first we introduce notation. So let us consider any matrices U and V of our dimension m by n. So of course it consists of rows u1, u2 up to um, and v1, v2 up to vm. Vm. And T will be some transitional matrix between these two matrices. So let it consist of the first m minus I rows of the first matrix and of the last I rows of the second matrix. So here it looks like this, that you take first rows from matrix U first, U1, U2 up to Um minus I, and then you continue with the rows of matrix V, up to Vm. And if you take Ti plus 1, then you do the same, U1 up to Um, and the difference is in this row only, on this position, and the next rows are taken from the matrix V. And we observe that if you take the difference of these two matrices, one minus the other one, then you get zeros, 0, 0, 0 here. Here you have a difference of these two rows between the matrix V, M minus I plus 1, and U, M minus I plus 1. And here you get again 0, 0, 0, 0. So the rank is equal to 1 or possibly to 0 if these rows are the same in both matrices. So this is the key observation which is necessary due to Marianne. So now when we have two matrices U and V, we also consider the special cases, the extreme cases. When we take T0 UV, we get the matrix U, then it is inside, in between, transition, and the Tm is the other extreme, it is the matrix V. And we observe, it is simple exercise, when we take the difference of these between U, so the difference here is 0, 0, 0, and here we have the difference between U and V in these rows, then the norm, the distance, is less than or equal than the complete difference between U and V. Here we have U minus V and so on. But here you replace it with 0, so the distance is smaller actually, not greater. the same if we take the difference with the matrix V by analogy, yeah, because we have U minus V and here we have zeros. So this is it. And now we consider the line segment spanned by the matrices A and B. So it is the convex hull of these two matrices depicted here. And we take a positive natural number L and divide it equidistantly by matrices as denoted S1, S2 up to SL minus 1. So it is as equidistant division. And in between, we insert these transitional matrices. These transitional matrices do not, in general, lie on this line segment, but as said before, they are close to the segment, yeah, because it is transition between these 2 points of the line segment, and the distance between of this matrix from the endpoint S0 and from the endpoint S1 is less than the length of this shorter segment S0, S1. So these matrices are close to the segment. And in particular, if you increase the number L, then all those matrices can be very, very close to the segment. Yeah? You get very, very many matrices, but very close to the line segment. So here it is written that the distance of each transitional matrix from the line segment is less than or equal than the distance from some particular points of the segment. And it is equal, it can be estimated by the length of the segment by the previous inequality, which holds in general, and it is equal to the 1 over L part of the length of the segment. It tends to 0. And of course, the second property, the rank of the differences is less than or equal to 1, yeah, because we have the transitional matrices. It consists of the several first rows of the matrix A, of the matrix S0, and then we continue with the next rows of the matrix S1, and we change the rows one by one, so then the difference between the adjacent transient matrices is, the rank is equal to 1, yeah, because they will differ by the one row only. So this is the main idea of the construction for the line segment, and we apply the previous recursive ray-fish colony construction on this object, on this line segment, and all in all we obtain that given some gamma and given matrices A and B, then there exists a Lipschitzian mapping H, which is finitely piecewise affine, and such that it is equal to the matrix AX, or driven by the matrix AX outside. This is the ocean around the rayfish. And in somewhere inside, deeply inside the construction, there is the last matrix B, and the derivative is equal to the matrix B inside. And when you travel through the entire recursive construction, then when the delta is let go to 0, then the M matrices tend to the matrices A, and this equidistant division on the line segment tends to the matrices on the line segment, and everything gets closer and closer to the line segment. So the distances of the derivatives from the line segment can be made sufficiently small by taking sufficiently fine division of the line segment. And next, we extend the construction for a polygonal chain. So we take many line segments connected each to the previous one, and we simply can continue the construction. In the first recursive construction, we start with the rayfish colony starting from B0 to B1, B1 being very inside. But actually, you can take the same construction from B1 to B2, again the rayfish colony, and then you simply shrink it sufficiently, you made it very, very small, and you shift it inside the previous construction. Again, you take this, again, construct it, shrink it, make it yet very, very small, and still place it inside there, and so on. And in this way, you can apply the same idea of the construction even for a polygonal chain. So here it is written in symbols. So given the matrices, we take the segments. Each of the segments is divided equidistantly by the respective points. And on each of the segment, we take the transitional matrices. Here it is listed. It is quite a long list. And rename all these long list as Q1, Q0, Q1, and so on, up to QLMN matrices, when n is the number of the segments of the polygonal chain, m is the dimension of the space into which we map, and L is the number of the points of the equidistant division on each of the segments. So we have very, very many matrices. The rank of their differences of consecutive matrices is always less than or equal to 1. So we can do the construction, and we observe that the distance of the matrix Q from the polygonal chain is always less than the maximum of the length of the segments of the chain divided by L. So it can be made sufficiently small as we made the division finer and finer. And we also observed that the rank of the difference of consecutive matrices is less than or equal to 1. So we can apply the construction, the previous construction, and we obtain this result. It is extension of the previous. So we have constant gamma, small constant gamma, B0, B1 up to Bn matrices. Then there exists a Lipschitzian mapping H, gamma, and so on, which is finitely piecewise affine, and such that it is equal to B0x on the ocean outside the unit ball, and on inside a very, very, very small, non-empty open set, very deeply inside at the end of the construction, the derivative is equal to Bn. And as we travel through the construction, we encounter all those derivatives, b0, b1 up to bn, and so on. And the distance from these matrices can be made less than gamma whenever it is differentiable. Because those matrices on the ray fish tend to the ocean outside. So that's it. So for this polygonal chain, the construction can look like this. So here it is the ray fish outside. Here is the ocean, and the other ray fish are placed inside for the all very, very long chain of matrices. So this set about which we have been speaking before is the very last open set inside the very last ray fish inside. And finally, we are approaching the end of this intermezzo. So we will introduce the corona construction. So we recall that for a constant gamma and for a chain of matrices b0 up to bn, we have constructed recursively the ray fish colony H for this polygonal chain b0, b1 up to bn. And this non-empty open set is very small. Here it is made larger so that we can see something. So now we make many copies of this colony, and we shift them and place beyond a sphere of radius 3, for example, or unit sphere would be enough also, in such a way that each ray or half-life emanating from the origin passes through at least one of these shifted open sets of the colonies, of this very, very tiny, very small set, which is very deeply inside all that construction. So it must pass through this very small ball inside, and all these colonies are to be pairwise disjoint. So when magnified, it could look like this. So here is the origin, and here we are trying to place the colonies, the ray fish colonies, the copies of this is still the same colony, but copied and shifted accordingly, and in such a way that each ray passes through at least one. Here it is good. Here it meets even two sets. So, yeah. Okay, so there are some questions in the chat. 5 minutes, yeah. Okay, so we continue. So when finalized, the corona construction will look like this. You take a so-called spherical shell, and you place those colonies in between some spherical shell. So you need a terrible number of the copies, a very, very large number of the copies placed in such a way that each ray emanating from the origin passes through at least one of the very, very small set inside. But it is possible to do it. And so we just obtain this lemma. So given a delta, B0, B1 matrices, then there exists ray B, rho and capital Rho, such that there is also a Lipschitzian mapping phi, finitely piecewise affine, such that it is driven by the ocean B0 outside of the spherical shell, and inside it is driven by the copies of the rayfish colonies as depicted on the previous slide. And moreover, because the mapping is piecewise affine, we have, if we take any subspace W, so we find a ball inside, we somewhere find a ball inside this spherical shell. Yeah, perhaps here, because it passes through the tiny set, such that the derivative will be equal to the last matrix Bn, and the distance of the derivative from the chain of the matrices can be made small, less than delta, whenever it is differentiable. Phi should be here. So finale. So we recall the question or the problem. Given a non-empty compact convex set of matrices, the purpose is to construct a Lipschitzian mapping G such that the Clarke Jacobian is equal to the given set, or moreover, even if we take a restriction on some linear subspace, then we still will have the equality. So we observe that when we take the non-empty compact convex set P, it is separable, actually. Yeah, so we can find a dense, countable dense set inside it, and it is enough to take a countable sequence of matrices, B1 up to etc., such that the convex hull is dense in the set. So you can take the extremal points, actually. And if some finite set would be enough, then we repeat the sequence infinitely many times for simplicity. So given the set, we consider the longer and longer and longer polygonal chains, and so on. We take a decreasing sequence of deltas, and we do the corona constructions for these chains with these deltas. So we have these, and so on. And you simply take the first corona, take the second, and shrink it sufficiently and place it inside the first one. And you take the third corona and shrink it even more and place it inside the previous, and so on. And it happens that the coronas will tend to the origin. So the construction could look like this. So this is the first corona for the first chain, B0, B1 perhaps. This is corona for B0, 1, 2, B0, 1, 3, B0, 1, 4 is inside, and so on. So all in all, considering we have the result being non-empty set, any non-empty compact convex set of matrices, there exists a Lipschitzian mapping G. It is countably piecewise affine, equal to 0 at the origin, and for every linear subspace, we have this identity at the origin. So this is the last slide, are references. So this, what I have presented, is in press presently in this journal. and it is an extension, perhaps as a continuation of the previous paper, which Marianne presented, I think, before at this seminar. So I should thank you for your attention. Thank you.
Thank you, David, for your beautiful presentation.
Okay.
Beautiful, both in terms of illustrations, which were beautiful, and also in terms of beautiful mathematics, indeed. So, quick questions. Do we have any comments, questions from the audience? Yes, Janusz,
So, first of all, we believe that Corona is not an appropriate name for this construction. We think it looks like sushi. And the second question is how can you be sure that you can pack everything dense enough so that you really hit them all the way you want to hit them? I mean, with the rays at the end.
With the radius.
Yeah, because you have these rays coming from zero. How can you be sure that every ray hits what you want it to hit?
Yeah, because it is hidden in this construction. Yeah, so the construction is that you take this. So this is very tiny ball. Yeah, this is very tiny ball. What you want to hit, and you first arrange it around this sphere. Yeah. So this small sphere is compact. Yeah, and this very small is open. Yeah. So you can place it into every point of this sphere. So you have infinite open covering of this sphere. So it is compact, so you can select a finite open subcovering. Yeah. So there exists. Yeah. So you have covering, and then you simply try to push it away. Yeah. You take the large ray fish around every, and you take one by one. Yeah. You have finitely many, so you take one by one, and you will finish in some time. So you take one by one, and you take the first, place it somewhere. You take the second, place it sufficiently far enough so it is disjoint, and so on.
Yeah, so my problem is that when you move them away, the angles get smaller, and then the covering argument is not so obvious anymore.
The covering, I see.
You see, that's my problem.
That's it. Really? The angles.
Yeah, then you introduce...
Yeah, you are right, actually. Yeah, you are right.
But maybe your compactness trick is good enough. Maybe you just have to play it on some
you are right. Yeah, you are right. I made a mistake in this presentation. Yeah, it is. Yeah, you are right. You must. It is not enough that you shift, but you must scale it. You must enlarge it.
Okay.
To get farther.
Yeah, if that then works with the packing, then I think I'm...
Yeah, sorry. Yeah, it is my mistake. Yeah.
No problem. You have to pack the sushi properly.
You must scale it. Not shifting, not enough, but scaling it. You are right.
Yeah, no problem. Thank you. Then I understand what's happening, I think.
Thank you, Janusz, for the contribution.
This problem. So maybe that in the presentation, not everything was for 100% correct, but this is normal. But if you have a look to the paper corresponding, then I think that everything is fine.
Yeah, in the paper it is correct. So sorry for my mistake in this presentation. I simplified it somewhat. inappropriately. My mistake.
May I make? Yes, it's. I'm really in a hurry. I have to leave in 30 seconds to take the train to not to miss my class. But I would like to make a very short question with a very short answer, yes or no. Is it true that every compact, non-empty compact, but not necessarily convex, set of matrices is the Boolean Jacobian of some mapping? Yes or no?
We don't know.
Okay. Sorry, I cannot. I have question, to leave. But... Otherwise, I will miss my class. Bye. Thank you.
Thank you.
Bye.
Thank you. More questions, comments? Who is not going to miss a train? David, just a very short comment or question, or maybe two closely related questions. These Clarke Jacobians were introduced almost 50 years ago. And such a fundamental question, which you've just answered, remained unanswered for almost 50 years. Why is that? Is it because it is a very complicated question, or Clarke or others were not interested in this? And one more question closely, maybe closely related to this one. Your presentation was about methodology, about this procedure, about this seafood with ray fish colonies and sushi or corona, whatever. And just a little, you talked a little bit about Clarke Jacobians. I'm just wondering if this methodology goes beyond what you've just established, and maybe it could be applied for other things. But I have no idea what things.
Yeah. So, well, both questions, I don't know what to say. Yeah, Clarke Jacobian, yeah, you are right. It is 50 years old concept, and it was by chance that we came across this idea how to show this result. And about this methodology, I don't know yet, so I cannot answer perhaps. So I don't know at this moment.
Yeah, I don't know. It's also an answer, the answer.
Maybe I could say something.
Marianne knows.
Actually, we are not experts in Clarke Jacobians somehow. And this question, which was answered positively here, raised some 1 or 2 years ago when we were writing the first paper. In the first paper, we, in particular, I should say that David was the main author of it, constructed a very specific potato, as I said, that is compact convex set in the world of matrices 2 by 3. And then we somehow had a big need to construct this special potato a Lipschitzian mapping. And in this first paper, we succeeded for this one concrete potato. But the general question remained open. And later, we realized that just very little was needed to add to extend our construction of the Lipschitz mapping in the first paper, that after some elaboration, this methodology, construction of ray fish, blah, 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 lead to answering, constructing Lipschitz mapping to any convex compact set. So this was our story. As I said, neither me nor David, by the way, David is an expert in Clarke lemma. I programmed in one species. We did not look for the answer to the question which was raised and solved here. Yeah. So this is how we came to this question.
Yeah, that's true. Yeah, the original question was really, we constructed some counterexample in our previous paper, and then was the question, is it a Clarke Jacobian of something or not? Yeah, because we had the counterexample and what? So then we tried to construct a mapping. So we succeeded finally, and then there was the idea was the next step for this construction, which was presented now, or has been presented now. So,
oh, very beautiful presentation and beautiful results.
yeah.
Any more questions, comments? If not, again, thank you very much for your presentation. Let everything be all right on your side. And we are looking forward to your next results and next presentations.
Yes. Okay.
Thank you.
Thank you very much.